Hi, Ashton.
Wagwan, man.
Yeah, we hope you're having fun at your debate tournament, but we couldn't stand the thought of you missing the washer method because, wow, that is so much fun. It's Halloween Friday and we're doing the washer method. It doesn't get any better than that. So, hey, you might wonder what on earth does the washer method have to do with what we were just doing with the disk method? It's when you got space between your region and the axis that you're revolving around. It's when you have open space. Now you can see on the screen here, I've highlighted in yellow the open space. You've got F and G as the upper and lower boundaries. You might notice I'm showing a big radius and a little radius. As you revolve that little region with the space, when you revolve it, you're going to have some open space in the resulting volume. Hence the name, the washer method. So you can see really what the author's done right over here on the far right. If you looked at a little rectangle between the two, it's that little rectangle that gets revolved with the space. It would create a washer shape. So that's the big difference. When do we use the washer? When you have some open space between your region and the line that you're revolving about. So let's go to this last page. And sometimes kids get a little bit nervous. Let's be honest, the washer method looks like it's more complicated. I want to point out to you that you're really using the disk method twice. You're first finding a big volume, and then you could subtract away a smaller volume. And I hope you can see that in this picture here, because that makes all the sense in the world. This yellow mass right here that I've just highlighted, imagine that I'd get a volume there. But then I'd say, ooh, I don't want that. Subtract it, remove it, take it away. So that's really what's happening with the washer method. It's taking your big radius. You always start with that, and you can pull a pi out from both of those. It's pi radius squared, but you can pull a pi out. And you take your big radius squared minus your small radius squared. The biggest mistake kids make, and I put a big star, the volume is never F minus G quantity squared. That would not be the subtracting of the volume. And if you work that out, you'll get some bizarre answers. Make sure you do two separate disk methods. A big radius, pi big radius squared, minus pi little radius squared. And if you remember that, you'll be in very good shape. So let's real quickly take a look at one such situation. So for number 4, find the volume of the region revolved around the given line or axis. Well, you know the College Board doesn't want to ask you to revolve around the x-axis, but we'll start there for simplicity's sake. And we could say, well, let's see where we're going here. Let me change this back to actually a black pen, perhaps. Let's see if I can do that. There we go. So we've got y equals x. Well, that looks something like this. I'm not even trying to draw it super accurately. If I had this other equation, I'd have y equals negative x plus 4, or 4 minus x. So I'd have a y-intercept all the way up here at 4, and then I'd have negative slopes. So you might guess we're going to look something like so. And we're going to also have x equals 0. These three equations right here are going to enclose this triangle. It's going to enclose right here. X equals 0, guys, is actually going to be the y-axis. So you've got the y-axis, you've got y equals x, you've got y equals 4 minus x. That forms this yellow highlighted region. And then they're going to say, would you revolve it about, I almost wish they'd always say about here, about the x-axis. So I guess the big question that we always have to worry about is, do we have the disk method or do we have the washer method? And the question is there space? Is there space between that region and where I'm revolving? And the answer is yes. Yes, there is. That means I need the washer method. And you could even do this to help drive home that this really is the disk method twice. You could say, well, if I went with a rectangle perpendicular on my low boundary, this right here is my little radius. That's my little radius. In another color, perhaps, maybe I'll go in blue, we could say, well, then won't you have a big radius? Yeah, it would look something like that. So we know we're going to have the washer method. We're also going to be integrating with respect to what? With x or y? What do you think? With x. You can see the stacking. If we kept doing that, we'd be going left to right. And that means I'm going to integrate with a dx. Of course, the big question is, as we're doing that, we're going to go from 0. Gosh, when y equals x and y equals x minus 4, let's set my y values equal and see where I'm going. If I add an x to both sides, I'd have 2x is equal to 4. X would equal 2. This would be the point 2, comma 2. And guys, I'm going to integrate from 0 to 2. Okay, and here's a pi. And then I'm going to say I need big radius squared. And I need a little radius squared. And I'll even write little r. And guess what? Ongoing, you're going to have top minus bottom. Top minus bottom for all these problems. So you'd say find the big radius. You could just look at the picture and very quickly see that the big radius is the blue rectangle. Does everybody see that? So what's top minus bottom? What do we have? Negative x plus 4 minus x. Do you see why you need this top minus bottom? Oh, no, it's not minus x. It's minus 0. Sometimes kids will say, whoa, why is it minus 0? Because the blue rectangle is a top of 4 minus x. The bottom is down here on the x-axis, isn't it? See that? The blue rectangle, it's from the top of this 4 minus x. The bottom part is actually on here on the x-axis. That's y equals 0. And then you'd say, what about the little radius? Well, we're going to do top. This is the red rectangle. What's the top of it? X minus 0. And, sometimes kids are like, I get it. The bottom is always 0. Who actually know that that's where it gets to be a little bit tricky. But that's why you want to draw pictures. That's why you want to be able to make this work out. So, listen, at this point, you could very quickly get this typed out on the calculator. I'll leave a pi out for the moment. And let's just do a math 9. And we're going to say we're going to go between 0 and 2. And I'm going to start off with some parentheses and say negative x plus 4. And minus 0, of course, isn't going to change anything. I'll say that's squared. I'll say minus, well then in parentheses we'll have x, minus 0, I mean it's technically just an x, squared. Put in your dx, and I'm getting 16. Final answer would be 16 pi. Okay. We doing okay with that? Yeah? All right, maybe we could set up this last one, hopefully. Y equals x squared. And then I've got y equals 4. Sometimes kids are like, we've already done this problem. No, we didn't. It looks like we did. It sure looks like we did. But now we're going to revolve around x equals 2. Oh my gosh. Wow, that changes everything, guys. That is going to get very intense. So let's see where we're going with this. Here's my region. right? Here's my region. And I'm going to be revolving that about x equals 2. So, wow, this is going to get to be a little bit trickier. First of all, as I'm revolving around x equals 2, would you agree that there is open space in there? There is. There's open space. By the way, this gets to be a much tougher problem. I think everybody's going to agree after the end that this is going to be a much, much tougher problem. As we're looking here, we do have space. That means we're going to have a washer method. Remember, our rectangles are always perpendicular. Let me draw a little radius. That right there is a little radius. It's going from the axis that I'm revolving around to the first part of the curve. Obviously, that's the small part. And then I'm going to say, well, you know what? I also want to be able to draw in a big radius. Because if I've got space, I've got that washer method. Here, I'm not putting it directly over it, but pretty close, just so it can be slightly offset and you can see it. That would be a large radius. Now, as you're looking at your rectangles, as they be getting stacked, do you think we'd be stacking them left to right or up and down? Up and down. Up and down. That means that my integral will be with respect to y. So that changes everything. It means everything inside of my integral should be with a y in it. And I'm trying to have more space. I'm going to need my big radius squared. I'm going to need my little radius squared. But maybe implicit in all of this, you should say, well, wait a minute. Here we go again. We've got y equals x squared. I really need to see other equations. I don't want to plug x squared into that integral. Look, if I've got y equals x squared, I could solve for x. X would be, help me out, plus or minus the square root of y. Guys, on the right of the y-axis, I've got this. X equals the positive square root of y. To the left of the y-axis, I've got x equals the negative square root of y. Wow. So let's go ahead and see if we could find the big radius squared. That's in blue. You can see the blue rectangle is much bigger than the red rectangle. What's the right boundary of the blue rectangle? Well, look at this right here. I'm touching it. The right boundary would be 2. You see that? So I'm going to say 2. What's the left boundary of that blue rectangle? Negative square root of y. Look, you're to the left of the y-axis. You're going all the way to the leftmost part to get that left boundary. That's the curve x equals negative radical y. So you'd have 2 on the right here, x equals 2. On the left, you've got x equals negative radical y, and then you've got to square it. Finally, we're going to say minus. What about the little radius squared? What would that be? The right boundary of the red rectangle would be 2. Minus, what's the left boundary of this red rectangle? Positive radical y. And I'm going to have to make sure this is squared too. That's your little radius squared. You could very quickly work that out. Okay, so we're going to have boundaries between 0 and 4. You know, you went from y equals 4 on the top, and you just type this in. We've already put it in, and hit enter. And, oh, I'm having technology problems. I'm getting, and it's thinking. We're in a race for time. Let's see if we can change that. 42.666 pi. So So that's how we work that out.